All right, so now we're just going to look at some AP problems to see kind of what types of questions you might see when you're doing graphing problems on the AP exam. All right, so they're small, but hopefully on your computer you can read them. So the function f is continuous on the interval 0 to 16, so continuity is always good. And it's twice differentiable, which means take the first and second derivative, except we're at 3, so that's our bad value. All right, information about the fur, yeah, that's given to us. At what values does the graph have a point of inflection? All right, so point of inflection means our second derivative changes signs. And it's only one place this happens. All right, when it's undefined at a place, that doesn't really help me, but the place that my second derivative changes from, oh no, that's, all right, what I'm looking for is my second derivative changing sign. So I have one place that's going to happen from positive second derivative to a negative second derivative. It doesn't matter what happens just at 3. It's just to the left of 3 and just to the right of 3, because I could have something that looks like that, and that would still be a point of inflection. So 3 is going to be one point of inflection. And I also get a negative to a positive at 9. So 3 and 9 are going to be my points of inflection. All right, at 11, I go from positive to positive. That doesn't change sign, so it's not a point of inflection. All right, next question is, we have this function at which of the following intervals of the graph both decreasing and concave down. So decreasing means our first derivative is negative. Concave down means my second derivative is negative. So we basically have to figure out both our first derivative and second derivative and see the overlap between them. So first let's do the first derivative. Be x squared minus 6x minus 16. And we want to set it equal to 0 first. You can factor it. So when we figure out when it's 0, that allows us to make a number line and put our important values on, our critical points, and do a test point in each region. If I plug in -5, I'm going to get a positive value. If I plug in 0, I'm going to get a negative value. I'm plugging all these into the derivative. If I plug in 10, I'm going to get a positive value. Right. So my function is decreasing in this middle region here between -2 and 8. Right. But I also need to overlap with the concave down, so I also need to figure out my second derivative. 2x minus 6. Set that equal to 0. Get x equals 3. All right, so 3, my test points. If I plug in 0, I'm going to get a negative value. If I plug in 10, I'm going to get a positive value. All right, so my second derivative is negative. I'm concave down to the left of 3. If I think about the overlap between -2 and 8 and to the left of 3, 3 would be there somewhere, and the overlap would be there. So between -2 and 3 is when my function is both decreasing and concave down. You can see these number line questions are going to come up a lot. Setting your equation equal to 0 to figure out the important values, and then picking test points to figure out your negative and positive for both of your derivatives. All right, the function f is differentiable and increasing on the interval, and the graph has exactly 2 points of inflection. Which of the following could be the graph of f prime? All right, so we're looking for f prime that has, will give us 2 inflection points of our original function. All right, so the first thing is we know our function's differentiable, so the derivative is going to exist, and it's increasing. All right, so if my original function is increasing, my derivative is always positive, which immediately eliminates this one. And then my inflection point will happen when my second derivative changes sign. So second derivative changes sign. But if I compare that to the graph of the first derivative, instead of thinking about this as the first derivative and this is the second derivative, let's think about this, the graph we're looking at, as the original function, and then the second derivative as its first derivative. All right, so that means the second derivative, when we're thinking about this graph, it has to do with increasing and decreasing. So if my derivative changes from increasing to decreasing, that means my second derivative will hit 0, which means my original function back at the beginning will have an inflection point. All right, so connecting all of these three together is kind of difficult, but again, for right now, I'm thinking about the graph as actually the original function and the second derivative as its derivative. So I want to go from increasing to decreasing once. This one is always increasing, so there's no inflection points, so that's not right. All right, this C graph, it goes from increasing there to decreasing there to increasing there. So my derivative function goes from increasing to decreasing, whereas my second derivative will go from positive to negative, which will cause an inflection point. So these two things are going to give me inflection points on my original. Here we go from increasing to decreasing to increasing to decreasing. This will give me 3 different inflection points. So the one that answers the graph, answers the question is C, because my first derivative changing from increasing to decreasing is going to give me an inflection point, and that happens twice. All right, this one's similar. All right, the graph of the second derivative of the function is shown. Which of these could be the graph of f? All right, so this is the graph of the second derivative, which is the graph. So the first thing we know, whenever we're talking about the second derivative, when the second derivative changes signs, that is going to give me an inflection point. All right, the other thing I know is here, when my second derivative is positive, I should be concave up like a cup. Here, I should be concave down like a frown, and concave up. So my function should start concave up, so that immediately eliminates b, because this is starting like a frown. All right, so b is out. All the other ones look good. From 2 to 3, 4, 5, I should be concave down. This one is concave up until about here, which means it doesn't switch early enough, so now this one is also out. All right, this is concave up there until about there. It looks like it's concave down. Concave up, that one looks good. All right, this one is concave up to about there. Then it's concave down to there, then up to there, down to there, up to there. All right, so if I look at all these functions, all right, this one has those 2 inflection points that happen at these same values, so C is my right answer. All right, so this unit kind of culminates mainly with this graph shaping stuff, but it connects a lot of things that we learned earlier in the unit, but really kind of making these connections between our second derivative, changing sign as an inflection point. How does that change the original function? My first derivative is increasing. That does something to my second derivative, which also does something to my original function. So making all these connections, I will talk about in class and kind of how to keep everything straight.